Even though our book starts at 7.1, 7.1 is just say, hey, we are in the land of conics, which means we are no longer in functions. That's all 7.1 is, done. I combined 7.2 and 7.4 because we are talking about circles and ellipses, and every single circle is an ellipse. It's a special ellipse, but not the other way around. Just like every single square is a rectangle, but not the other way around. There are properties of squares and rectangles that share, and that's the same thing with circles and ellipses. So when we're talking about conics, it basically says we have two cones stacked on top of each other, tip to tip. How you slice the cone is going to determine the shape of your conic. Now, if you have the first one and you slice the cone at an angle, and you only hit one cone, you end up with a parabolic shape. If you slice one cone and one cone only, and your slice is parallel to the base, then you have a circle. If you have a cone in which you slice it but it is not parallel, you have an ellipse, which is kind of like a squished circle. The last one is you slice your cone twice straight through and you have something called a hyperbola. We are going to be exploring first the circle and an ellipse, and then we go back under the parabola and hyperbola. So the parabola is 7.3 and the hyperbola is 7.5. We only do 4 sections in here because the first section is, hey, this is what a conic is. They're not functions. We are out of the land of functions for a while. After we get done with conics, we are going to explore, and it'll be the best thing we've ever done, polar equations. So we're going to explore polar. We're going to go from rectangular to polar, and then we're going to explore conics in polar form, which is so much easier. Then we're going to go back and we're going to finish out chapter 11, and in which time we are going to be doing vectors. We love vectors. It'll make your life easier if you know vectors. And that will pretty much finish out the quarter. So let's talk about a circle in general. So we have our general, we're pretty familiar with our circle equation. Our circle equation that we talk about on the unit circle all day long is x squared is equal to x squared plus y squared is equal to r squared all day long. This is a specialized circle. In fact, on the unit circle, r is 1, and we are centered at 0, 0. For the most part, we are not centered at 0, 0, so we won't be using that very much. The one that we do use is x minus h, the quantity squared, plus y minus k, the quantity squared, is equal to r squared. So this is where the center is not at 0, 0. The center of my circle is h comma k. So we have moved the circle off of the 0, 0 origin, and it is no longer at 0, 0. And in fact, when it's at 0, 0, it is not interesting. So we take our conics, and in particular our circle, and move it off the origin. What that means for us is that we get to complete the square twice. So we take a look at this example, and we want to know if you are given the equation x squared plus y squared minus 16x plus 14y plus 32 equals 0, is that we need to take this equation here and turn it into this equation up here, which means we get to complete the square twice. It will be the most fun we've ever had, especially when we start putting multipliers out front. So let's go ahead and go through this example of taking this equation and putting it into standard form. So I start out with x squared plus y squared minus 16x plus 14y plus 32 is equal to 0. First thing I do is I reorder it so my x's are together, my y's are together, and anything that doesn't have an x or y gets kicked to the other side of the equal sign. So I rewrite this as x squared minus 16x plus y squared plus 14y is equal to negative 32. Now you will notice that I left some blank spaces there. So what I have to do is I have to complete the square. And I need a perfect square trinomial right here. I need this to become a perfect square trinomial. And I need this to become a perfect square trinomial. So the way in which I figure out to find a perfect square trinomial is, first of all, I got to remember what the heck that is. So if you have a squared, a squared plus 2ab plus b squared, this becomes a minus a plus b, the quantity squared. That's a perfect square trinomial. Or if you have a squared minus 2ab plus b squared, that's also a perfect square trinomial. So I need to take these right here that I underline in blue and red and make them perfect squares. The way in which I do that is I figure out what I need to add right here, and also, let me just erase this so I can move this over a little bit. What I need to add right here. So what I add to one side, I better add to the other. So I need to figure out what I need to add here and here. Yes?
Is that where you do 1/2 of b squared?
1/2 of b, and then I square it. So b is this value right here. So I take this, negative 16, I divide by 2, which is negative 8, and then I square it, so it's 64. So I'm adding 64 right here, and I'm adding 64 right there. That makes this side become x minus 8, the quantity squared. So I've completed that part. I'm going to do the same thing for the 14. So I take 14, divide by 2, and I get 7. I square that, and I get 49. So I add 49 here and 49 here. What I end up with then is plus y plus 7 squared is equal to, and it is, I don't know, what is 49 plus 64 minus 32? You all have calculators? What is it? 64 plus 49 minus 32. 81? Thank you. So what I have is I have a circle with a center as 8 comma negative 7, and a radius is equal to 8. And this is where we're going to kind of cruise from the last of this quarter, this kind of stuff here. So this is like, man, I love this, I enjoy this, cool. The worst part is over. If you're like, I hate this, well then, we still have 3 more weeks of this kind of stuff. Have a great day. Yes? So let me erase that. It should be a radius of 9. What we're going to be doing today is we're going to continue on with our circles and our ellipses. So let me just make sure that I can get rid of the stuff I don't need, and then we're just going to continue on. What we were doing yesterday is we were working on circles. Now circles are a special kind of ellipse. What an ellipse is basically a squished circle. With an ellipse though, we have more information. We have the major and minor axes. We still have the center, so we still have the same center. We have a center in which we were looking at a circle, so we're still going to have some center, and it will be h comma k, just like it is for our circle. But we also have major and minor ellipses, or major and minor axes, and we have something called foci. So up until now, we didn't have to worry about foci. And the way that we actually define the ellipse is a set of all points whose sum of the differences are the same from a foci, which is a constant value. So you'll notice that we have here, we have our ellipses on the 0, 0 is where the center is at the origin. I have them labeled foci 1, so you see F1 and F2, so a foci 1 and foci 2. We will find these letters C. We'll find exactly how to find those in a moment for any ellipse. Your major axes are the ones that are the largest distance from the center. So these are your major. And then these, the shorter distance, is the minor. By convention, your majors will have the A's attached to them, and your minors will have the B's attached to them, by convention. So I'll give you a moment to write that down. We're actually gonna give you it in generic form too. So one of the places you will see an ellipse is if you are going into the medical field. You will have this device, I don't know how to pronounce it, so I'm going to butcher it, lithotripper, something like that. And what it does is it helps get rid of kidney stones without having to actually go in and have surgery on them if you can't pass the kidney stones. So, and it goes in an elliptical shape. So as it goes around in an elliptical shape. You will also see it if you ever have the opportunity to go into Salt Lake City, the Mormon Tabernacle in Salt Lake City. And they do let non-Mormons in, by the way, because they let me in, and I'm not a Mormon. In fact, some probably think I'm the Antichrist, but I'm not, and they did let me in. I didn't burn, neither did they, so it's all good. The other place you'll see it is if you go into our Capitol. So our Capitol building, if you look up, it is an elliptical shape. And the reason that elliptical shapes, and in this case this is a parabolic shape, is because you all can hear me without needing for me to really shout. So the reason we make these shapes is if you stand in the foci of an ellipse, or you stand in the foci of a parabola, then you can talk and speak without using a microphone. So if you look at any of the opera buildings, the theaters, the old theaters, used to be that if you were standing on the stage, then you were standing on the foci, so it allowed you to hear it without necessarily having a microphone, because back in the day they didn't have them. Yes?
Foci is the center.
No, foci is this number here, and we're going to figure out where that is. So that's the foci, yes?
Next to the A, is that the one and a half?
So,
I just can't see the small one.
yeah, it's like a little apostrophe.
It's a,
Oh, that's the, so that's just saying it's a prime, it's just the lower part. It's just the lower part of the left side. Yes?
Is the foci only on the major axis?
Yep, the foci is only on the major axis. We're actually going to go in depth in this in a minute. Our solar system is an elliptical pattern. It's not a perfect elliptical, but it is an elliptical pattern. So here's how we define or how we get all of the values. So if we are at the origin, this is what it looks like in standard form. It is x squared over a squared plus y squared over b squared. Now a is the largest number, so whatever is the largest number is going to tell you where your major axis is or running parallel to. In this case, a is the larger number, is underneath the x. So because a is the larger number and it's underneath the x, it's divided into the x part, then that tells me that my foci and my major axes are along the x-axis. Okay? So let me say that again. Because my larger number is a, and it's underneath the x part, it's divided into x squared, that means my foci and my major axes are on the x-axis. The way in which we find our c value is c is going to be equal to the square root of, or in other words, c squared is equal to a squared minus b squared. It's the larger number squared minus the smaller number squared. Your vertices, and when we do the vertices, we are usually talking about the major vertices. So if you just see where are the vertices, they're asking for the majors, not the minors. The majors, because again, we had it as x squared over a squared plus y squared over b squared is equal to 1. Your majors are along the x-axis. So you'll notice on the vertices that are given to you that they are the x part of the x-intercepts. Your minors are along the y-axis, and those are your y-intercepts. So notice that it is plus and minus b. A is the distance from the center to the origin, or center to the major vertice. So A is the distance from the center to the major. B is the distance from the center to the minor. And C squared is not Pythagoras at all. It's actually a modified Pythagoras. We're used to A squared plus B squared is equal to C squared, and it is not. It is C squared is equal to A squared minus B squared. And C is the distance from the center to the foci. So that is C. How are we doing?
C is the distance from the center to the foci?
Yep. Yes.
Will these notes be published on campus?
Aren't they published now?
No, they're not.
Oh, okay. Yes. Yes, yes, absolutely, yes. Sorry, yes, they should have actually popped up yesterday, or actually last week. So yes, I will go in and trigger those to show up. Yes?
So we're just trying to understand. So foci is the distance between your large value, the x-axis for this, right? And then on the smaller or the minor axis, the foci for that, what was that called? Is that still the?
We only have one set of foci, and they're on the major axes.
Okay.
And the foci is the distance from the center to that point. Now, when we're talking about an ellipse, so let me erase a couple of things here. So when we're talking about an ellipse, is this distance here, if I add those two together, that's going to give me the exact same distance if I would have added those two together, which gave me the exact same distance if I would have added those two together. So that's how we define an ellipse, is that they're all the equal distance from two positions that are not changing. So that's what the foci are. If we're not given the foci, which typically we are not, then the way in which we find the foci is we use this equation. We almost are never given the foci. We're being given an equation and then we're asked to graph it. We'll be asked to find the major and minors, and we'll ask to find where the vertices are, and we'll ask to find the center and all that stuff. Does that answer your question?
Yeah.
Okay. Now, the other way that this can be is if my larger number is underneath the y. Here, my larger number is underneath the y, and now my major and my foci are running on the y-axis. A is still a distance from the center to the major vertice. B is still the center to the minor vertice, and C is still the distance from the center to the foci. So this is still A, is still this distance. It's just now along the y-axis. This is still B, the distance from the center to the minor. And this is still C, the distance from the center to the foci. Those don't change. It's just the direction in which they are. They don't change. They're still distances. The other thing that doesn't change is where I get C. How do I find C? Well, C is still going to be C squared is equal to A squared minus B squared. Notice now, though, my vertices are along the y-axis, and my x-intercepts are my minor vertices. These are my minor axes. The length of my major and my minor haven't changed. The length is going to be 2a and 2b. Those don't change at all. Questions? Anything? Anything at all? How are we doing? It's Tuesday. It's Tuesday. 3 weeks from today, all you have left is your final. 3 weeks from today, all you have left is your final. Okay, so let's go ahead and run through this information. I'm going to do one of them. You all, I want you to attempt the other one, and then we'll go through it. Which one would you like me to do? A. Okay. So as I'm running through this, they're telling me the foci are along the x-axis because those are x-intercepts. So that tells me my major must be along the x-axis. They're giving me that C has to be 2. So I'm going to draw a picture because I love pictures. And I'm really good at drawing. Ha ha ha. So at -2 and 2, these are my foci. I'm going to put that information down there. I'm trying to build the equation. Now, it's telling me that I am centered at the origin. How do I know I'm centered at the origin, even though it doesn't tell me that? How do I know? Because my foci are on the x-axis. Because my foci are on the x-axis, I know I'm at the origin. The other thing that they're telling me is the major axis has a length of 6. That 6 is equal to 2 times my A. Because that's how we define the length of the major. It is 2 times A is the length of the major. 2 times B is the length of the minor. So that tells me my A must be 3. So I come up here, and that means from my center, I have to go 3 in each direction. These are where my vertices are. Okay, so I know where my vertices are. I know where my foci is, and I know that my center is at 0, 0. The next thing I have to do is actually figure out what the equation is. Now, the way that we write the equation in general is x squared over, in this case it'll be a squared because my foci are along my x-axis, plus y squared over b squared is equal to 1. Now I have the a already. I'm chasing b. So I have a. I have that value, and I need to chase b. The way in which I chase b is I know that a squared minus b squared is equal to c squared. Or c squared is equal to a squared minus b squared. It is the modified Pythagoras' theorem. So I know what a is. I have a replacement for a. That is 3 squared minus b squared. I have a replacement for c. What is c? Well, that's the distance from the center to my foci, so that is 2 squared. So then what I have is 3 squared minus 2 squared is equal to b squared. So 9 minus 4. So this is 5. So I'm just asked to find the equation. I'm not asked to graph this. So I'm not going to take that extra step and take in the square root of it, because what I need here is b squared. I don't need the square root of b. I don't need b is equal to, so I'm not going to take that extra step. Is it wrong to? No, it's not wrong to. I'm just not going to, because I'm not asked to graph it. So what I now have is x squared over 9 plus y squared over 5 is equal to 1, and that's it. That's it. So I want you to take a look at what I did. Ask me if you have any questions. Yes?
Can you explain more kind of just how, what you used to do the 6 equals 2a? and
Okay.
then,
So what they told me is that my major axis has a length of 6. The total length from beginning to end from vertex to vertex is 6. We have this formula that it doesn't matter which way I'm directed, the major axis is 2 times a. And it doesn't matter which way I'm directed, the minor axis is 2 times b. So that tells me down here that 2 times a has to equal 6. Whether I want it to or not, it has to equal that length. And that means I have the a value. Anything else?
How'd you get B?
So I have this formula that doesn't matter which way I'm directed, this has to hold true all day long. C squared is equal to A squared minus B squared. I have C, I have A, I'm chasing B. What else? Yes? Yep, this is it, right here, done. Isn't that sweet? Oh, we have to graph it too? Okay, we can graph it. It's no big deal. I erased my graph that I started out with. So let's just put that information back on there. So here were my foci at -2 and 2. These were my foci. My A value was -3 and 3. And then my minors, this is where I guess I have to do the square root of 5. So B squared is equal to 5. That means B has to be plus and minus the square root of 5. And without a calculator, I just know it's more than 2 and less than 3. So somewhere more than 2 and less than 3. So the square root of 5, negative square root of 5. And now I'm just going to connect that very, very well. That's a beautiful ellipse, isn't it? The best ellipse you've ever seen. There it is, in all of its smooth, beautiful glory. Yes?
I was just wondering where the foci of the solar system is.
I don't know. I'll have to find that out. Or actually, you know what? You find that out and let us know. Okay, please try B then. So, my vertices, unless it tells me these are my minors, if it just says vertices, by default they're giving us the majors. So I always draw a picture of this because I need to know which direction I'm going in. So 8 and -8. So that tells me my A is 8. Right out of the gate I know what A is. And it's going to be underneath who? The X or the Y this time? The Y. Because my majors are on the Y-axis or along the Y-axis, so it has to go underneath the Y part. So what I have so far is Y squared is over 64, that's 8 squared, is equal to 1. And then I have X squared over. Now I'm chasing the B. They tell me that the length of the minor axes from side to side is 10. So then for this one, I have 2B is equal to 10. So what does B have to equal? 5. So that means there is my equation. So if I only needed the equation, that's all I had to do. Now, because they're asking me to graph this, I do need to find my vertices. So there's 5, and here's -5. And to find my vertices, I have this rule that says it is C squared is equal to A squared minus B squared. So C squared is equal to 64 minus 25. So C is equal to plus and minus. And what is 64 minus 25? 39. So my foci are the square root of 39 up and the square root of 39 down. And they should be as ordered pairs, but I can't shove that in there. Square root of 39, well, that's bigger than 6 squared, but it's smaller than 7 squared, so it's somewhere between 6 and 7. Okay, I don't have that, so I just know it's somewhere between 6 and 7. Any questions on that? How was that? Hopefully not too bad. Now, we are going to move off of the X and Y axis. Our centers are no longer going to be at the origin. So what I know is no matter which direction I'm going, H is attached to the X, just like it is on the circle. The K goes with the Y. Doesn't matter which direction I have my majors and my minors. But what does matter is H needs to go with X and K needs to go with Y. Now, the distance from the center to the major is still A. It's still A. The distance from the center to the minor is B. The distance from the foci to the center is still C. The only thing you have to pay attention to is those numbers need to be added to the correct parts of the center. if my major is along or parallel to the x-axis, then I take my A and add that to my H part of my center to find my majors. My minors, right here, are going to be H, comma, and then K minus B, and H, comma, K plus B. Because I'm adding those values to the K part. Because my minors are running parallel to the y-axis, so they're going to be added to the K part. My foci, because they're running parallel to or on the x-axis, my foci are going to be H plus C and H minus C. Yes?
I think I missed where the H plus A, comma K comes in. What was that?
So my center, I'm going to erase all of this. My center is now HK instead of 0, 0. The distance between my center and my major is still going to be A. So that distance is still the same, and what's changing, as you can see, I drew a parallel line to the x-axis, so the y does not change. So to find where my majors are, I need to add and subtract the A from the H part of the center. My center before was 0, 0, so I didn't have to worry about doing plus and minus H plus and minus A because it was at 0, 0. Now I'm not at 0, 0, so I have to do the plus and minus from the x part of the center. The same thing is going to be true when I'm doing my foci. Notice that line that I drew in your eye and my eyes, that's parallel, exactly parallel, to the x-axis. So my foci is going to be my H part of my center plus and minus my C, because my y does not change. And then to find my last piece, which is my minors, notice that that line that I drew is parallel to the y-axis, which means I need to add and subtract my B from my K part. So to find those minors, my minor axes are going to be, on this case, it's going to be H, which doesn't change, K plus and minus B.
And the majors is K plus or minus?
H, because K is the Y value. Y is not changing because I am running parallel to the x-axis.
Can you just write that? Is that?
Yeah, these are right here.
Oh, yeah.
So when we are talking about it in the other direction, the only thing that changes is A is underneath the Y. The larger number is underneath the Y part. And now I add and subtract from my majors, I add and subtract from the K part. My foci are added and subtracted from the K part. My minors are added and subtracted from the H part. So it's the opposite of what we just did. So it's the opposite of what we just did. Scroll up this way. Remember, I'm directionally challenged. And these are all on the formula sheet too, you know. Or you not, you don't know that. Yes?
And so this is, an ellipsis is from like slicing a cone?
Yes. So we're slicing a single cone, but not parallel to the base. So I'm slicing a single cone, not parallel to the base. And I say slicing a single cone because when we do hyperbolas, we are slicing two cones.
So does it matter like the angle that you slice it?
Mm-mm.
Just your foci, everything will change?
Mm-hmm. All right, so here it is in the other direction. Again, these are all on your formula sheet. So let's actually do one of these. I'm going to do D. I'm going to do D because I'm going to complete the square and it will be the most delicious thing I have ever done in my entire life. So if you were asked to find the equation in standard form, the first thing you're going to do is rewrite it 4x squared plus 8x plus 3y squared minus 6y is equal to 5. You're going to rewrite it so that your x's and y's are together. The next thing you're going to do is rewrite it by factoring out the coefficient on the x squared part. So it's going to be 4x squared plus 2x plus something. And then I'm going to do the same thing with a y. So plus 3y squared minus 2y plus something. This is going to equal to 5 plus. Now, I am multiplying 4 times that blank spot. So on the other side of the equal sign, I need to have a 4 multiplied by that blank spot. I am multiplying 3 times that blank spot. So on the other side of the equal sign, I better have 3 times that blank spot. Now, I do my normal completing the square. So I take this value right here, I divide it by 2, I square it. So if you divide this by 2 and square it, I'm going to add 1 here, I'm going to add 1 right there. This then becomes 4x plus 1 squared. It's a perfect square trinomial. What is 2 divided by 2? Square it. So I'm going to take this, divide it by 2, and square it. So I'm going to add 1 here and 1 here. So then this combines down into 3y minus 1 squared. Yes?
Do you know the negative on the top part of y is negative 2y?
So I took a negative 2 and I divided it by 2 and squared it. So on the other side I get 4 plus 9, or 4 plus 5 plus 3, so that's 12. Now, this is not in standard form. I am almost there because this thing has to equal 1. This has to equal 1. So I'm going to divide everything by 12. To have it in standard form, it has to equal 1. And so this is going to be x plus 1 squared over 3 plus y minus 1 squared over 4 is equal to 1. Where's my center? Negative 1, 1. Where's my major? Is it parallel to the x or parallel to the y? It is parallel to the y because this is the larger number. We'll finish this off tomorrow. Have a great day.